Hello, welcome. And what's the task today? So, as I was saying, last time we had some serious things, but out of the board. So, one, but two is that I changed somehow my decision. I wanted to say just the base idea of proving the independence of continuum hypothesis, and then move on and then see the real proof when we got to sheaves. But then I thought that okay, so we have that problem. See, now I'm out of focus for no reason. I'm just alone, right? Thank whatever. But then I thought that okay, maybe this is the best idea to do this. But using H sets, we can prove really prove the independence of CH here without going to sheaves. With sheaves, we prove the independence of axiom of choice to have different flavors of things. And also, I need to say something about the last construction and using it to prove something about independence or consistency in constructive mathematics of some things. Therefore, I repeat the continuum hypothesis part in detail with more structure, more than just the intuition today. But before that, just recall that what we had, right? If you remember, we had the topos E, and I told you how to interpret a first order language when you have different sorts like sigma 1, sigma 2, etc., and then quantifiers with those sorts. We saw that how to interpret these things inside one topos, right? And also specifically, we saw how to interpret it in H sets. We saw something about the quantifiers and the interpretation as the big conjunction disjunction here. Then I said that okay, I can use it for arithmetic, for instance, or algebra or whatever, when you have some fixed objects, and then you prove construct your model. But then what happens for set theory? I said that in set theory I have two problems. One is that I have unbounded quantifiers, so they range over all possible elements of all sets, and that is not friendly with my setting of interpreting first order language. The second thing is that if you think of the objects of a topos as sets, some alternative sets, then more or less you have everything. You have power set, you have, right, because you have exponentiation, and therefore you have also omega. Then you can think of PA as A to omega, right? Am I right? No. Omega to the A, always wrong. So all maps from A to omega, then all the subsets of A. So you have power set, you can think of your basic axioms like constructions of union, whatever. But the problem. Can you say a bit more about how set is working? So what is in the realm of topos theory, right? What is a subset is subobject. And then any subobject, we saw that it is kind of equivalent to a map from A to your subobject classifier, right? This is the characteristic map. So if you know, so omega here is subobject. Yes. And then this exponentiation just collects all possible maps from A to omega, and therefore it's it is 2 to the A in the world of topos, right? No extra work to do to kind of make this behave like a set on somehow a different kind of object from the other object or something like this. What do you mean? It has some properties based on the fact that it is exponentiation and the guy is object classifier. So you can work with them universally and prove things about your PA. It is not any set or any object. I don't know. So for instance, you can prove that there is one map from A to PA like a singleton, right? That mimics the singleton idea. Or there is a map from PA times A to omega that reads some subset, reads like some A, and decides whether A is in the subset or not, right? Things of that sort.
Maybe I don't remember how you're interpreting set theory in the top. So you're going to say more about?
Yes, I'm trying to say something very wrong about it. So the idea is that I don't want to pick one object here and pretend that this is the whole universe of set theory. I can do that, but I don't like it. The idea is that I want to find some sort of interpretation such that any object here can be interpreted more or less as a set.
But object, really meaning object.
Object means real.
So not arrow.
No object. And
so in your, you said that A going to PA is like a singleton.
yeah, there is a map like
so
this.
what is the object of the singleton?
Yes. Okay. Many problems. The thing is, in set theory, you can have sets and objects of sets, right? Which are sets themselves. This is allowed in set
theory.
theory.
In set theory as a task?
No. In set theory as, set theory.
Elements.
Yeah. Everything is a set. That's the point in set theory, right? But here you have objects, you have arrows, different sorts, etc. So what you have to do is kind of to deal with all these things together. So the point is that you pick. Okay, let me explain it here, and then I come back to your thing, right? So yes, I said that every object here should be interpreted as a set. But at the same time, any element of that object, meaning morphism from one to that A, should be also a set, right, etc. But to handle this thing, you need the following kind of construction. So what I was trying to say is that how to handle these unbounded quantifiers, how to handle the foundation axiom, right? That says that everything is well-founded, because everything else is kind of given, right? Via the suppository construction, we can construct everything from below, but there is no need to be, for anything to be reachable from empty somehow. So you have to handle your foundation. So the trick is this. For any alpha, as I said last time, you define your V alpha as one object inside it of what? And the definition is that V0 is just a zero object. And V alpha plus 1 is P in this sense of V alpha, right? So object to object. And then V of any limit, of course, is just the limit of all, or the union, if you like, but whatever. So alpha is limit, then all beta less than alpha. So I assume that my E is complete, therefore I can construct these things. Now, when I say for any X, for any set, I interpret it as first for any set in V alpha, for some alpha. But then I mean for any alpha as well, right? Therefore, I interpret it like this. So then, to answer your question, what is a set? It is all the elements in all V alpha. And then what is, when I say that something is inside another thing, so that epsilon thing, right? This is epsilon. That something is inside another set. So here, everything lives in V alpha. So you pick V alpha, you have these two things, and inside V alpha, you have that interpretation of something is inside something else. So that's more or less the idea. But it is just full of many details that I'm just ignoring. So my main point is that universal or existential unbounded quantifiers should be bounded, but for any ordinal. And since I'm constructing everything from below, then I get my foundation, right? I'm not saying how, I'm not saying how to really interpret the language of set theory via this trick. I'm just saying the idea of it, right? Because it is kind of a mess. Right. However, the point is that whenever you want really to prove independence, and people did this, so that the point is that you have to construct, for instance, let's say that is it possible to use topos theory to prove the independence of CH from ZFC? And the answer is yes. The point is that you have to construct some complete topos. Usually it is, so in this case, for instance, it is just a Grothendieck topos, therefore complete. You construct a topos E such that you know some good property like refuting CH in some informal sense. But then you have to come back to this interpretation if you are serious about it, to interpret inside that E all the things inside your language, satisfy ZF. Usually ZF is for free. C is not. C should be checked. You know, if you start with some complete topos, you get your ZF via this construction, but not always C. Therefore, you have to also have some sort of, you know, axiom of choice for E. We saw one external version of it. For instance, to prove this, for instance, it is enough just to pick E such that any epic splits, right, as we had before, and then you get your C. But then you get the topos theoretic version of C. But if then you come back and interpret really the axiom of choice, as it is in set theory, via this trick, you see that that topos theoretic version of axiom of choice helps to show that it satisfies, right? So there is some topos theoretic version of things that helps via this interpretation to satisfy the set theoretic version. This bridge I'm not covering because, you know, there's no reason to do that really. But you can simply see. And my goal today, at least for the CH, is just to construct some E. First, to explain what do I mean by having, you know, a model of C. I said actually now, right, that this E, whatever it is, it should be Boolean because it should be classical. To via this trick, I have ZF. Therefore, it should have that external axiom of choice, EAC that we saw. Any epic splits, but it doesn't solve anything. It is just a general machine to construct something like ZFC. But the main thing is just to refute this guy. I need a categorical version of CH, and then I have to refute that. And something that I'm not saying is that how to use this interpretation to transform the usual CH really to this CH, the categorical version, right? So my task is first, let me explain what CH means really in a topos, right? In a topos-friendly language, and then construct a topos failing this VDS. So what is CH? CH in set theory is what? It says, okay, the failure of CH, say, that we are interested in. Okay, so we want to construct a model of the failure of CH. Is what? So I have the usual set theoretical thing is that you have your natural numbers, you have its power set in your set theory, and you get the failure of CH when you get some set in between, and in between means that the cardinal of this is less than that, but the cardinals are not the same, right? So I have to rewrite this in terms of the topos theoretical language, right? I can do one, I'm not sure. Okay, let me do this. What is n? I never said anything about natural numbers in a topos, right? Always I said that you have, you know, product, coproduct, blah, 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 but yeah, subsets, everything, but nothing about natural numbers. If it is a real set theory, if it is a foundation of mathematics, you have to have your natural numbers. Coding natural numbers in this topos theoretic or categorical, probably it's more meaningful to say, categorical way to say what something is a natural number object. It's called natural numbers object, NNO. The definition is simply this. So you have a category C and one object N, so object N. But again, it is not enough to have one object. You have to also have some structure. So the structure is that you get one map. from 1 to n, probably we should call it z. This is just picking the element 0. You have successor from n to n. That's your successor function. So the whole data is called NNO, not just the object. The object, that map, all the three. The whole data is called NNO when it is universal with this property, with this structure, meaning that if you start with, say, so this is your 1, this is your z, this is your n, this is your successor, this is your n. If you pick any a, any f, say 1 to any a, like probably that's a better name, g and h. So the similar structure, right, with another a, then this is initial, meaning that there is a unique map f such that, so of course there is one map here, right? So what is it? There's that, so such that you get the commutativity, right? So it is initial algebra in this sense, initial object with one map and one map from one map from there. So theoretically, this is just something easy and we all know it, right? This f is just iteration. It simply says that on 0, define f of 0 as g, some element in A. So g is an element. So I'm simply saying that f of 0 is g. G is just one element in A. And then I'm saying that f of n plus 1 is defined as h of f of n. Right? What I'm saying is that n with these guys is some object with the property that for any picking g as element in A, any function on A, you can iterate it uniquely. Right? And more or less, this is the property of n, right? Because uniquely means that it is the least inductive, and the existence simply means that, you know, it's freely constructed by all these things. So that's the definition of n. Like any other universal thing, you can prove that it is unique. Simply put it itself, put the other one here, and then you get one map, the other map, the composition should be identity, etc. NNO is unique up to isomorphism. This is the categorical notion of natural numbers, right?
Axiom saying that as x is never equal to 1, or you already stated it.
You cannot put, yeah, that is good. You can, somehow it is here, but it is not that explicit. How it is here? Because, you know, if you get a loop, right, that's just a problem, right? You start here, plus, and then you get a loop, then that's bad for defining your f, right? Because f should be freely defined whenever you set your 0 and you set the other things. If you get some, you know, if you get back, then I get a clash between two conditions. And some, yes. Yeah. So for instance, if S is identity, then what? Then that's something else actually. No. So you said S of nothing is 0, right? You said S of nothing should be 0. That's different. So here also you satisfy that. If S is identity. Okay. S of 0 is 0. Yes, that's bad. Okay, fair enough. So let's say that S of 0, for instance, is 0, right? Then I have a problem. What is my problem? The problem is that this construction simply says that you can define f of 0 as anything, and f of successor of n in terms of f of n, and probably I can then define f of successor of f of 0 as 0, for instance, always, and f of successor of everything as 1, right? So if S of 0 and 0 are equal, then 0 should be equal to 1, right? So the point is that this recursion scheme simply says that S0 can be anything, successor can be anything else. And there is no connection between the two. And therefore, successor could not be 0 because there would be a clash, right? I'm not free to choose. But it is not the whole power that you want. For the whole power, you need more structure, really. Right? So it's not exactly capturing whatever. So for instance, I have no induction really for n, except that I have some more structure. Induction in the sense that, the usual induction, but don't use just, use the sub-objects. If I have sub-objects such as closed under something, then is it the whole thing? I guess you get this, but you don't get some other thing. But anyway, so my point is that this is the categorical version, and whenever you have enough structure, you get all the usual things. So this is my n. Okay, fair enough. Now I have my n here, right? If it is enough to have some e with an NNO, not all the toposes have NNO, right? But finite sets. Finite sets is small. The category of finite set is a topos. But common, there is nothing infinitely big there, right? So it is possible to prove. And but all the categories that we constructed before, like all the sheaf categories, H sets, etc., because they are structured on set, always they have their NNO. And
These, how are they related to the ordinal indices?
yeah, so natural number object in the toposes that we care about are very low. Exactly like the natural numbers in set are low, right? So the rank is low.
But the indices that
Yes.
live in your original model of set theory,
Yes. Yes.
and you could construct more ordinals, I guess, using this NNO somehow.
Yes.
And would they be the same as those indices?
Not necessarily. For finite, yes. For infinite, no. Because that's the whole point, right? You can change the notion of cardinal, really, and ordinal also. When you go to bigger models of certificate. But always when I mean that, I mean external. So I don't care about internal because I can.
When the indices.
Yes.
Okay.
Always they are external. Okay. So this is my n. Fair enough. I have my n. Not always, but sometimes you have, as I said, your NNO. And one example probably is this. In H set, what should be the NNO for any H? It is just extremely simple. N and the obvious equality of n. This equality is a map that goes from n times n to H. If they are equal, 1, not 0. Right? So you can do it for any set, actually. You can pretend that any set is actually H set, right? Simply by defining equality like 0, 1. No other intermediate things.
So you're writing down the NNO again?
Yes, for H set. For this category, I'm claiming that the NNO as object is this.
So the NNO is two objects.
No, it's just one object.
One object.
No, it is. Yes, one object, two morphisms.
Okay, you haven't said the morphisms.
No, but morphisms are also obvious, right? Because one here in this category we saw, it is just singleton with obvious equality. The map just picks 0, and this map just goes from successor to successor. And yes, they are just usual functions, not H-set maps, but come on, this is just the usual equality. Of course, always I respect that equality, and it is total. So you can, whenever you want to check that everything is okay, so you end up checking it in set, really. So,
does it work in general if you have category like this that you can construct this NNO by just taking the terminal object and making like 1 plus 1 and plus 1 and this and then it's or there's a problem.
If your category is complete, then yes. But sometimes that thing does not exist, so no.
But you mean complete just in the sense that you can form the polynomial of the chain?
Yes. Yeah, set small like polynomial. So, okay, so that is my n. Now I have my n. P of n is meaningful in any topos. It is just n to omega to n, right? All the subsets of n. So now, what do I mean by this guy in the topos, right? So now we are doing something risky to go to the other board. Okay, thank you. And okay, so it is also easy. So what is this in set theory? This card, this means that you have less element here than in B, right? And the formal version of this, of the cardinal thing, without saying about ordinals, cardinals, whatever, is just what? So this means simply the existence of one injective map from A to B. So then I can mimic it in any category, right? So this simply means is there exists one monic M from A to B, right? And okay, fair enough. And what is this? This should be probably is A is less than B, but not isomorphic to it, right? Not with the same cardinal. Or you don't like it? This is my definition, but probably if I want it to be well behaved, I need that contour Schroeder-Bernstein thing. And I will explain. But this is my definition. I can't do any definition, right? Yes, yeah.
The isomorphism would just be a mimic interaction, right?
No, isomorphism is something with inverse, right? So there is no two functions as inverses from A to B and B to A. But you're right. So depending, you are going from one natural setting to the other, and then you have to find the most natural one. I would say that this is the most natural one, but there are many really different versions of this, and then they are not equivalent in general, of course. But why I'm saying that this is okay, the point is that cardinals are not that good, well behaved. However, in our case, everything is fine. So you are right. And while you are right, at least let's see. So if I'm free to choose my definition, I would say that this is the natural definition, this is my definition, whatever. But then you may say that, okay, if it is your definition, then you probably expect some properties, including, for instance, this. Right? That if I have a chain of things also there, if one of them is just strict, then it should be strict, right? That is a very natural way of ordering things. But this is not trivial, really. You need contour Schroeder-Bernstein for that. So let me just forget about this and then talk about CSB, contour Schroeder-Bernstein. So CSB, which is true in set, simply says that if A is less than B and B is less than A, then A is equivalent isomorphic to B, right? That's a property that we have in set. This is not true in toposes. And counterexample is this guy. In set to 2, this is not true. And I can write and explain all the details about this. Probably I won't, but maybe I have to at least say what are the A and B's, right? So let's say that we leave here. You remember that every object here is just a map. So I need two maps, one monic this way, one monic that way, but they are not isomorphic, right? And monic means, because we are in this category, everything is pointwise, so two maps are monic. So the two objects are this actually. So two functions I need is a set. And one is that mapping n to n half, the integer part, of course. And then this is n to n plus 1 half. Right? These two ugly maps are just two objects in my capital, right? And there are two monics, one in this way, one in the other way. Yeah, one is just because it is n plus 1, this is n. Simply, I guess this one is just n to n plus 1. Then you change the base. And the other is n plus n to n, but you have to be careful about 0. I don't explain the maps between the two, but believe me, if you play with this, you see it, or you're not.
What happens in the range?
What do you know?
What the upper arrow?
In what case?
In the first one, let's say. You go from left to right. What's
Yes.
the upper arrow?
If I go like this, I guess it should be n to n plus 1 as a map, n to n plus 1. Yes, because it is n to half, and then you go plus 1, and here you plus 1 of this. No, it should, I guess. That's some, no, start here, right, with some n. Then I come here, it would be n plus 1 half. No, it should be n plus 1 here. Then follow this. It is n plus 1 half, right? Which is just n over 2 plus 1, which is n over 2 plus 1. Right? The problem is that these are confusing. So think of them like here. Right?
So here, that is 3.
Yeah.
First of all,
Yes. This is 4, 2. Yeah, the point is that you have just plus 1, and over 2, it would be just plus 1. Is this. And the same, okay, not the same, but I guess backward you should go from n to n, but it doesn't work for 0. For 0, you have to go to 1 or something.
But the natural one would be that you go from n to n plus 1 downstairs, the upper way, and we have just identity on that, and just do this difference between n plus.
No.
but if I send 4 from the lower left corner,
Yes.
I either get 2 plus 1, 3, or I get 5 divided by 2 rounded down, which is 2. So it does not come here.
You are starting with 4. And come here, it is 5. 5 plus 1, 6 over 2, 3. Huh? There is one backward, just believe me. Yeah, it is okay. So my claim, please check, and if it is false, then tell me. The backward should be n to n, as far as I remember, n to n for n at least 1, but 0 should go to to 1.
The thing on the right is literally composition. You first do plus 1, and then you do the same thing as on the left.
Yes. You are right, but the point is, okay, whatever. It is possible, just right. We are kind of out of time. But they are not isomorphic, at least. These two guys are not isomorphic. Because what? Because peak. So again, this is n to n half. This is n to n plus 1 half, right? And then they could not be isomorphic, because if they are, then there is f and g such that these are isomorphism, and then everything commutes. And that is kind of impossible, because it is isomorphism, then 0 is covered by exactly one element, which is m. right? And M comes from 2M and 2M plus 1, two different things. But 0 here comes from simply 0 and not 1, right? It is unique. Because 0 goes to 0, but 1 goes to 1, and etc., right? So 0 is covered simply by 0, and then two things comes to 0, and that's bad. Whatever, I don't care.
Well, if it is, then it does not have two pre-images.
At the point, okay, even if it is 0, then it is 0 and 1. Right? So, yeah, yeah, thanks. Good. And it is not focused, not on me, not on the table. So it is just focused on what? I guess if you change it to 1 and come back, then it solves the problem. As far as I remember, it was like this. Okay, whatever, thanks. Okay, so point is that you can just do your exercise and prove that it is not true in any topos. But there's a theorem that I want to use, and I don't want to prove that if your topos E is Boolean, then it satisfies CSB. So whenever you are in the classical realm, you're fine. So the problem here is that it is intuition. The converse is kind of true, not really, but the converse probably. So you expect that if you CSB implies Booleanness, right? That's not true really, but if you have N and O, then it is, right? So more or less, because always we have the N and O, we are in the big setting. CSP is kind of encoding, this guy is encoding Booleanness, being classical. And whenever you are not classical, there are millions of different ways to define the strict one that are not equivalent. But we don't care, right? We are in the Boolean case always, because we want to construct something for ZS. Anyway, so if you have your Contra-Bernstein thing, then this lemma is true. That's simple, right? Because of course, A is less than or equal to C, because monic composition is monic. But then they could not be isomorphic, because if they are isomorphic, then what does it mean? It means that I have A less than B, at least, and B is less than C, but A and C are isomorphic, and therefore B is less than A. Cantor-Bernstein says that they are isomorphic, but they are not. So if I change these two and strict here, I get the same thing. So strict then is well behaved, if you like. Okay. So now I have everything to say my CH. What is CH? It simply says that find E, okay, negation of CH, probably. There exists object A such that you have an N is N and O in your thing, such that this. You have a Boolean topos with an N and O and one object between them. So there is a monic from this to this, monic from this to that, but these are not isomorphic, these are not isomorphic. Or if you like, there is not monic on that backward, because you are doing Boolean, so they are equivalent, right? So I have to construct this topos.
So it's saying there is some NO for this property.
All of them are isomorphic to each other, therefore there is DNNO. Okay. But if we, so I could just ignore the NNO part to say that I'm refuting the generalized continuum hypothesis. It is just enough to find something, its power set, and something in between, and that something could be anything, right? But I'm refuting more, so probably I have to say. Okay. Let's keep this and go back and construct this E. We construct this E before. I want to write it and also then explain exactly the proof of that, because we had it roughly but not really. So how to construct E? You remember that I explained the idea. The idea was this: work. So E, your E, it should be B set for some Boolean algebra, and therefore it is Boolean, right? 1, 2. Now, as I said before, we know what is an N here. So therefore, N equality is my N and O here. So I start here. I have the, so let's call this guy N. And then I have the power of N, which is omega to N, right? Inside B set. And remember that omega, the subobject classifier in B set was B and equivalence, right? That B set. And then I want to find something in between. That's my goal, right? But something is B set when and everything is internal to that category, meaning that there is a monic in the category, monic in the category. They are not isomorphic in the category, right? So, and what was my intuition? Intuition was that start with some very big X, like this is a set, usual set X as power set of natural numbers, something big. And then use this X to construct a very big B. And that big B helps to what? Since every sub object here in the category is a map from N to omega, and your omega is just that big B. Since B is big, there are many maps into B, and therefore there are so many sub-objects, so many subsets. And if it could be very big, then I can find something in between. That's the idea. And that between thing kind of comes from this X, because X is the force to make everything big, right? I use this big X to construct big B, then probably something based on X is in between, right? And that's it. But very formal. Yeah. How to construct? Before that, I need a lemma again. What is the lemma? The lemma is what? The lemma is, so what's the intuition behind the lemma? The lemma is something like, we want to construct some bad things in B set, right? And bad thing is a strict thing between some sets, some B sets, right? The main idea that I had is that pick some very big X and then force everything such that blah, blah, right? So this being big inside set means that you have some strict inequality in set, right? When I said that this is so big, for instance, N is less than this, or P of N is less than this inside the usual board, right? This is 2 to aleph naught, right? And then aleph naught and 2 to aleph naught, they are strict. So this bigness, I have to preserve when I go from set to B set, right? Because then I can, I need some way to transform data from set to B set to use there. And that data is strictness. So first I need a lemma to go from set to B set, and then I do something also in B set, because it cannot be completely inside set, right? Because we don't know it. That the continuum hypothesis fails there. So the lemma is this. So keep this, check that. And what is the lemma? The lemma is this. That's for any B, it should be B. Lemma. Okay, first, there is a way to go from set to B set, right? There is a functor here. The functor is, as I explained, right? So you start with set X, whatever it is, and then f of X as B set here is simply X and the obvious equality that if two things are equal, then it assigns 1, otherwise 0. And for functions, just choose the function here and then prove that it is a B set function. Come on, it's just obvious, right? So this functor maps set to the bigger set, right? The bigger order. Lemma says that if B has some property, F preserves strictness. Not always, but sometimes it preserves strictness. So if B has, say, the Suslin property that I will explain in a moment, then F, this F, preserves strict order this, i.e., if you for any set, you know, x and y, if you have this, then f of x is also less than f of y. So that is some interesting lemma. Probably you know your Suslin property, right? The Suslin property simply says for B is that if you have a set for any set subset S subset of B such that for any A and B inside S, A and B is 0, of course, for any A and B different, then S is countable. Right? It says that you have your Boolean algebra. If you can pick, you know, some objects, some elements, such that any two of them does not intersect with each other, then the whole thing should be countable, right? Your B is not so big. It is big, but not widely big, right? Yes, also. Yeah. And anthropologists call it Suslin property. Okay, so if my B has this property, and then later I construct such a B to have this thing, then I have this. How to prove it? I prove something else, and it is cute theorem. So first, I guess it is enough to prove this. Let's say that proof it is enough to prove this. Is it really? I want to show that it reflects. Of course, right? Because yes, if s, first, if x is less than equal y, of course f of x is less than f of y. Simply because this map from x to y is 1 to 1, and then it is easy to see that this guy is monic, really. So that's it. So then let's say that this is not inequality, they are isomorphic. Then there is a map monic from f of y to f of x. And then if I have this, then I have a map from y to x. Then I have Cantor-Bernstein, Schroeder-Bernstein instead. Therefore, they are isomorphic, which is not the case. So therefore, it is simply enough to prove this. It is enough to prove this, right? So, and the reason is that this is something negative. This is something positive, right? It is better to work. So how to prove that? That is kind of cute. And of course, I have to use my SP. This is the proof. Let's say that I have f of x, f of y. Then I have x, equality of x, 2, y, equality of y. There exists some map G inside B set, and G is monic, right? That is the definition. Goal is that the cardinal of x is less than the cardinal of y. Right? I have to do some counting to do this. It is set. So we have just the usual theoretical language, coordinates.
The assumption or.
The assumption is this. What is f of x? It is x plus that obvious equality. And the same here.
Is G the origin?
No, it's just a monic map by definition. So this means that there exists a monic map. G is the monic map. So, okay, I have a monic map. Let me then go to the other board and use this monic map to prove. Let's see, everything is okay. Yes. To prove that everything is okay, right? What do I know from this monic map? So since it is monique and it's a map, I have the following two properties that I want to use. So one, it is a map, so it's a functional thing, but probably the one that I care is that for any x in x, for any x in x, the big on y of gxy is 1, right? Because you remember, right? The functions are total, so if x exists and x exists means that e of x is less than this. E of x is always 1 because x equals to x in that obvious equality. So then I have this, right? And the second condition is that it is f is monique, and we had the lemma without proof, of course, that something is monique if and only if it has the following property that gx1y and gx2y implies the equality between x1 and x2. But in the natural language, it will be what? Because this is just the obvious equality. Either it is 0 or 1. If it is 1, I don't care. Always I have this. The whole information is that when it is 0, simply when these two guys are not equal 1. And then this guy must be less than 0. Therefore, simply I'm saying that this is 0. Right? That is the other condition that I have. So now, slowly you can see my Susslin property. So then what? Then let's prove it. What do I want to prove? I want to prove that the cardinal of x is less than the cardinal of y. How to do it? Here is the trick. First, let me prove something, and the claim is that for any y, for any fixed y, pick all fixed y, pick all the x's, fixed y for any y, pick all possible values of this apart from 0, right? And go over all the x's. This set is, of course, countable because of this condition, right? I have countable. Also, I have to say that for different x's, I get different g's here. So the map from x to the values are also 1 to 1, simply because if I have for different x's, I get the same g, then the same g and the same g become 0. Therefore, that g is 0, which is against my assumption. So simply I'm saying that for different x's, I get different values, and all the values are countable by that condition, right? Because I have this, right? So there are countably many x's with non-zero g. That's the thing that you have to learn. So now some obvious counting. Do this. This is x times y, right? So this is x. This is y. And then on x and on y, you write just 1 in this cell whenever g x y is non-zero, right? So how many ones I have in the whole picture? The others are 0, right? How many ones I have? So for any x, one of these guys should be non-zero, because if all of them are zero, then you get 0 equals 1, which is not the case. So 1 is non-zero. So in each line, at least you have 1, 1. Then at least you have cardinal x, so number of ones is at least x, right? Because on each line, I have at least 1, 1. But it is at most what? For any y, the number of x's with this property is countable. So it is cardinal y times countable. If I assume that my y is infinite, then this, okay, so by think it is this. And if y is infinite, then it is this. And I proved what I wanted. But then it means that I had to change that property that I forgot. So coming back to this guy, f preserves strict order on infinite sets. I ate this. So that I forgot. Okay, that's good enough, huh? Now let's come back to this construction that I promised, right? So what is this A then? I have to pick some B, and I have to pick something in between. And my B probably should be Boolean, of course, and it should have that Suslin property because I want to use this theorem. And then if I have these things after I constructed my B, whatever, then I get something good. That something good is this. So here is the base idea that I have, and I explain my B and the construction later. So first you start with this big X. 1, 2, you get this strict, then let me write like this. This is in set theory. It's equality, sorry. Less than x equality of x. So why? Because these three are strictly below each other in set n 2 to the n by Cantor's theorem, and x, which is 2 to the n, right? So they are different in set theory. And therefore, since I assume my B without any, we don't know the construction yet, but B should be Suslin, therefore I have this. I have a strict, and all of them are infinite, of course, right? Okay, perfect. Huh? Yes? And then if I construct this, so if I manage somehow to pick my B or my omega based on x such that I get this guy, I get this much power set, subset, but inside, so it is not enough to have, a monic map from X really to all the power sets. It should be some monic map inside. Then I get what I want. So my A in between would be this guy, not this guy. Because of the lemma, right? This is strict, right? That's fine. This is strict, but non-strict composition is strict. Then this guy is really strictly between the two. That is what I have to do, right? So as you can see, we have all the things. Only thing that I have to care about is just to pick Suslin B such that I have this, right? This is only task that I have. And so rest is just some, universal kind of argument. And now this is the Cohen force. So for the B that I want to describe now, construct the category of B set, which is a topos, and then that topos is called the Cohen topos. Because it is exactly the topos theoretic version of the Cohen forcing for the continuum hypothesis. Okay, let's do it. Right. So here's the idea. You have your big X. You define your P as the set. These are the things that we had before, but I will, I explain again. So that is the set of all finite partial maps, of course, partial because they are finite, as you can see now, like from x times n to 0. You remember that we want kinda to have this, and therefore the idea is that is it possible to find, a monic map from x to 2 to the n, and because I want to force it somehow. But the point is that, of course not, because x is so big, there is nothing like that. But all the approximation, finite approximation of that, because any function here is just a map from x times n to 2, they all exist, right? Pick them and construct your b from them, and that b forces these guys to exist. So this is my p. Order is just a subset order between functions, right? The restriction. So I have now order p. This is what we usually call the positive of conditions enforcing, right? And it's exactly that thing. So 1, 2. And what is my, so remember, we have to construct our B. This is the only task that we have. So what is H then first? Our H for H sets is offsets of P and OR. This is opens our topology, therefore it is a Heyting algebra, it is complete, we saw it, blah, blah. But not necessarily Boolean. We should Booleanize it. The Booleanized version is H double negation, as we had last time. So all the opens such that double negation of U equals to U. What is double negation? If you open up the definition, because it's a Heyting algebra, it has implication, then you can see what, so I have to open it up. So the point is that P is inside double negation of U if for Q bigger than P, there exists R bigger than Q, R inside U. So that's usually called being dense, right? Okay. So now, based on the general things that we had before, without any mention of the P, as long as P is some posted, everything goes fine. And then we have just some Boolean B. And therefore, we can construct our B set, right? Okay, fair enough. Now I have to check two things, right? One is this, because now we have the tuple. And two is that B has really the Suslin property, right? So okay, checking the Suslin property is not that hard. So let me just skip it. So we can just write down some, detailed proof, but not that hard conceptually. That really cannot find more than countable things. The main thing probably for us is forcing this, and this is what I have to do, because my time is somehow limited. So, and I want to say something about arithmetic as well. So if you go from X to, okay, so I have to construct some monic, and that's the only thing that I have to do, right? So what is the monic? Last time I explained the monic function actually like this, right? I said that go from, so what is Pn? You remember all the maps from this n. So this is just, somehow as a set, it is just a set maps from n to b, right? Any map from n to b, because it is equality, it respects everything. Any map from n to values is just one subset. And then we construct a function like this, if you remember. I said that map x to rx, and rx should be a function from n to b. So read this, find all the p's such that p x n is 1, right? All the p's that forces, they say, right, that condition. And then it's not that obvious. We have to prove that this is really in B. Of course, it is upset because if Pxn is 1, then everything above it is also 1. That's upset, that's for sure. But it's not enough. It should be also double negation stable, right? Should be dense somehow. And we can, we did, but let me do it again. We can check this condition that if for any Q after P, there is some R such that Rxn becomes 1, then Pxn is already 1. And the reason is just very easy, right? The reason is that assume that Px1 is not 1. It's either 0 or undefined because it's a partial function. If it is 0, for any Q after that, it remains 0. And of course, for any R after that, it is 0. And I can find some R such that it gets 1. That's a contradiction. So you decided to fail at P, and if you decide to force to 0, then you cannot change it to 1. Never. If it is undefined, you have also a problem. Since it is undefined, then it means that I can define it in any way that I like. I go to the Q above P and I assign it to 0. And then again, there is nothing after that I can make it to 1. So the point is that this simply says that any way up, there is some point up that becomes 1. So in all possibilities, eventually you come 1. That's what it says. And the stability simply says that if you eventually become 1, you have to be 1 at the first place because otherwise, always I can change it to 0. So that is really big then. Fair enough. The only thing that I have to do is to show that this function is actually not 1-to-1. We checked last time that's 1-to-1, but it doesn't matter. It is actually monique as a map P. And what does it mean? This is the last thing for this hard thing to go with. So, okay, this map is 1-to-1. It's monique, sorry. What is monique? Monique means that if you open up the definitions, etc., it means that if two things, the values are equivalent here, the value of it is less than the value of equivalence here, right? So according to B, it should be isomorphic. So what does it mean? It means that the value of Rx being equivalent to Ry for any n, because these are two functions. So this is for any n, these two guys are equivalent. This value must be less than the value of x equals to y. And x equals to y simply means what? Means that either they are equal or not. If they are equal, it's fine. If they are not equal, the only condition actually that I'm putting here is this. That if x is not y, if they are different, then it is not just enough that Rx is different from Ry as a function. That is the usual moniqueness. This guy is 0, right? The value is less than the value of equality here, which is 0. The value should be 0, not just. So, So I have to prove that this set, which lives in B, is 0. So let's say that P is here. So if P is here, then P is in any n is here. So then P is here if and only if here, meaning that P of x1. So let's say that P is something, and then P is here if and only if Px1 is 1, if and only if Pyn is 1 for any n, right? If P is here, then you have this, if you open up everything, right? Being P inside this means that Px1 is 1. Here it means Px1. So it's more than that. For any Q above it should be, but you get this at least, right? And there's a problem here. P is something and it's finite. If x and y are not equal, of course I can find some very big n somewhere where I'm not saying anything about, right? Because T is finite, right? It cannot say about all the numbers. And make one to 0, the other to 1, because X and Y are different, right? So it is impossible to find P here, right? This simply says that finite information cannot capture the whole picture, right? The forcing condition is finite. And then I get the Monique map that I wanted, and I get really construct something to fail the CH. What happens to Z? So ZF, I said that we always have via that thing. What about the C? You remember that I said that B sets, whenever B is Boolean, always satisfies C. We had it before, therefore we have C. So that is the Cohen model. Okay, so since the construction is exactly the same, not exactly what's kind of, probably I have to say also something about arithmetic now to you know close this part of the game. In arithmetic, arithmetic is easier because really I can construct a model of arithmetic, right? I can just pick one B set via the streak, B for some Boolean algebra, and then that one B set would be a model of, there's no need to go for all of it. Okay, so how to do this? The idea is, okay, what I want to prove is the Paris-Wilkie kind of thing, the forcing that says that this cannot prove PHPR. So what is I-open? I-open simply is that the language is the language of arithmetic. You have successor, you have plus, times, etc. Probably no, etc. Also 0. And an open formula is just transfer free. R is a binary relation that I add to the language. We know nothing about it. It is generic. And then I open is just any open formula, any quantifier free formula you have induction for. That's the theory plus some basic usual axioms for addition, multiplication, blah, blah. That's the theory. PHP is the pigeonhole principle for R. Pigeonhole principle says for R that for any, so roughly speaking, it says that for any X, R, which is a relation, can not be an injective total function from the elements. This means that the elements less than X to the elements less than or equal to X, right? If you have more pigeons, then you cannot map them to elements. And R, simply it says that PHP R is that R cannot be that function, right? There is no function because R is generic. R cannot be that function. So what I have to do is just again do some B set kind of thing. B Boolean because everything should be usual, Boolean arithmetic. 1, 2, no. 2. I need some object here and some maps, blah blah, to make it into a model of I open of R. Of course, R is something that I have to interpret. Remember, R is a relation. Therefore, it takes value inside B. It's not just true or false, right? And exactly like that being big B there, I have that power, that B is something, and I can control my R based on that B. That's the point. So how to construct the model? The model is like this. Usually they say that that's my version of it actually, but doesn't matter. More or less, it is Paris-Wilkie. So you pick some non-standard model of arithmetic, meaning that it is equivalent to n, but it is non-standard simply because there is some C in M such that it is non-standard, meaning the part that I need is that the points below C is infinite. I use this. This is crucial for me, right? So N is just a model of arithmetic, let's say true arithmetic even. but it is non-standard. Therefore, there is some element non-standard. Therefore, every the set is infinite from outside. So, what is my B then? Then I need my P. What is my P? P again, like what we had before, is I cannot construct a one-to-one function, right? But I can construct all partial one-to-one functions. So then all finite partial, this time injective functions like from C plus 1 to C. Right? It maps the elements less than C plus 1 to elements less than C in an injective way. You cannot do that, but you can do it partially finitely. Okay, fair enough. Order is just the usual order of the functions again. What is H? Exactly the same, opposite. What is B? Double negation H. Huh? I want to make it classical, right? Again, with the same trick. One thing that I have to mention before I'm going to the details is that when we go from, so what is the big join and big conjunction H? It is intersection and union in the offsets. But it is not the same for B. The intersection of the stable double negation stable things is double negation stable, and therefore it is here. So then, big conjunction is just intersection again. But big disjunction is different, right? Big disjunction is not necessarily if you do your disjunction over some stable ones, it is not necessarily stable. You have to stabilize it. And the stabilization, therefore, is that the big disjunction here simply is double negation union, right? It is your. And therefore, what does it mean? It means that whenever I'm in B set and I want to interpret there exists something, for all is easy, it is just opening up, but there exists is after double negation there exists. Okay, so is it enough? No. What is my B set? This is my B. Fair enough. What is my B set? B set is M and just the obvious equality. Equality like 0, 1. I do not. The point is how to pick R, right? And we know how to do it, right? So the structure should have, of course, it should have some plus, times, etc., because this is how you interpret first order language, but you do it just according to M. And since equality is just the obvious equality, there is no problem, right? Everything is just fine. All the axioms are fine. The only thing that matters is that I added one R, binary R, and I have to interpret that binary R. How to interpret it? It should go from your word, binary, so your M times N to B. That is how you interpret relation, right? So therefore, the interpretation of R must be what? Must be mapped from M times M to your B, right? And you have to define it. So what it should be? It simply says that read M and N, two elements in the non-standard model, and then pick all the P's that they believe that M is N, as we had before, kind of the same thing, right? So M goes to N when you cannot say that M goes to N or not, but the only thing that you can say is that the value is all possible finite data that says, finite conditions that say that it happened. Again, R should be in B, right? This value should be in B, therefore it should be stable, right? So what is stable again? So you have your P. So simply I'm saying that if for any Q above, there is R such that R of M becomes N. So here always R of M becomes N. Then R P of M is also N at the very beginning. Let's see. So either P of M is defined. Okay. So either you have P M is N, that's fine, or P of M is something else, or N is P of something else, right? Either this pigeon goes there or you know. So in each of the other two cases, then if I get up, I preserve all the conditions, right? And if in the middle I force, M to go to, even there's no need. If M, for instance, goes to something else like N prime, then never I get M equals to N, right? So what I'm saying is this: if P of M is defined here and it is N prime, which is not N, right? Then it's bad simply because everywhere up I preserve this data, but it says that eventually it becomes this R of N becomes N, but then it is also N prime, and therefore it's not function, right? And the same also goes when P of something else becomes N, because then up you get some function, but it is not injective. So that's something bad. Therefore, it simply says that either P of M is N here, or it is simply undefined. But if it is undefined, so you have no information of something going to N or M goes to something else, then the problem is that here in Q, I can force M to go to something else, right? And there is no bad condition because we know nothing about M and N, right? And then up, I cannot make it M to N, right? So this is just playing with the definition to show that it is in B. Fair enough. Now what I'm saying is that this model M, this is a model of I open R, but also it says that PHP is wrong. And by this, I mean that the value of all the axioms here is 1, but the value of PHP is not 1, actually better, it is 0, right? So this is easy to show. This guy is easy. Because what is it? It simply says that pick C as your thing, and then I want to show all the three, that for any x, for instance, less than C plus 1, for any z less than C plus 1, for any y less than C, if R x, y, and R z, y, then x equals to z, right? This means that it is a function. There is another one similar that says that R is 1 to 1, but the main important thing is that it is taught. That is the hard one. Right? So to check these guys, because for all opens up, right? It is just intersection, it is just and, big and then intersection. Simply I'm saying that picks 3 elements, right? 2 less than C plus 1, 1 less than C, and then this must implies that. And therefore the value of this is less than the value of that, right? So what does it mean? It means that if P is here and P is there, then these two guys are equal, right? But if P is here, then P says that X goes to Y, P says that Z goes to Y, and P is just a function. We always said that, therefore these two guys are equal. P always, as a finite thing, is injective. Then you have also the second one. The main is this, right? Because of course we can construct functions, partial, finite, from C plus 1 to C. That's fine. Totality is the bad one, right? So how to check the totality? The totality is this. It simply says, remember, existence is double negation. It's not just the usual existence, but this is just for all. So the only thing that I have to prove is that for any M less than C plus 1, this guy, let's say N less than C, R Mn is 1. 1 means the whole P, right? Everything is forcing this. How to do that? This is double negation of union. Simply I have to show that for any P, for any Q beyond P, there exists R beyond Q, this is just double negation, and there exists N such that Rm is N. Right? So P is not in, this is not union. If it is union, then P of M should be N. It does not say that. It says that eventually P of M becomes N, but for different N's, right? So they can change. So how to prove this? Pick just any P, pick any Q above it, who cares? The point is that this Q just either says that M goes to something or it doesn't say anything about M. If M goes to N, just pick that N and always above it have it. If M does not go to anything, just pick some very big N without any clash because it is just so big, right? I can just add the condition and there is no clash of being injective, and therefore you satisfy it. The last thing that I have to say is that it is actually a model of I/O. And here I would be kind of okay, let's do it. So how to do it? It's a model of I open, meaning that induction is induction quantify free, but you can have R, and induction is this, right? So that is true for your M, and meaning that the value, B value of this is less than the B value of that. The B value of this, so if you write this down, then you have the values, you have intersection. For all is just big intersection of all M's inside M. That is M, that is M plus 1, the value of these guys. And this should be less than the value, the value of any AM, right? Because this is just big conjunction. Yeah? For any M, I have to prove this. And A is quantify free. The only thing that I know is this, right? Okay. How to do that? Here is the trick, the usual forcing lemma trick. The trick is this. If M was standard, then M is a number, 5, 4, whatever. I start with 0 and I go up to I reach 5. The problem is that M is non-standard and I don't know how to reach, except that I have induction, right, inside my M for definable things. Therefore, I have to show that this is definable in the following sense. So I show that P inside A of M bar for any A, not just A, so let's say B, such that B is Q free. This is the whole thing is one statement about M bar, right? Phi of, let's say, phi P of M, phi PB of M bar, right? This is definable. I can find a formula to describe this. Whenever B is quantifier free. Why? Because quantifier free is just conjunction, disjunction, blah, blah, blah. Everything is just there, except the atoms, right? For the atom, equality is just equality, the obvious equality, so I don't care. The only problem is R and its negation, if I do it in a very Boolean way, right? If I do R and its negation, then I have disjunction, and then that's fine. I have conjunction, sorry. And disjunction is bad. Disjunction is double negation. Double negation is going up, and it involves all the Q's. Also, universal is bad because it involves all the Q's, and these all the Q's are all the finite partial information, all the finite parts of M. You cannot axiomatize that. You cannot define. So the point is that it should be quantifier free, or it should be E1 also, with some tricks. But so the only thing that I have to do is this: P inside R of Mn must be definable, and P inside negation of R Mn should be definable in terms of M and N, and then that's fine. Because then I say, if I do this, I say that, let's say that P is here, right? Then this formula is true for 0 if you fix your P. It is true for any M to M plus 1. Since it is definable, it should be true for anything. It should be true for M. Therefore, the only thing that I have to do is just to show that this is definable. This is, of course, definable because it simply says that Pm is N. whatever your coding is for finite data, this is definable, of course. But what about this? This simply says that for any node upward, it is impossible to go from M to N. And any node upward is any extension finite, bad for definition. However, you can reduce, the negative is also forced there. How? So the point is that you can show that this is equivalent is actually to PM is defined as some N prime different from N, or P of some M prime is N, M prime is different. They are equivalent. Of course, if I do something bad about P, then that's bad, upward. But if something bad upward happens, then I get this, right? So do you believe this, or I have to explain? I have to explain. Huh? The point is this. Let's say that at some point above, right? Which part is hard? This implies that. That's true, but I have to do. Okay, so you believe this, right? Please believe this. Yes. So, but the whole point is that negation is really based on the forcing is something going for any finite part. The whole point is that you can reduce it. You can decide being positive or negative with finite data, and therefore it is definable, and therefore you are fine. So that's also a very important point about your forcing. Thank you very much. Bye bye. And this, because it takes time.